Hello, my name is Chris Harris and I'm from Allery Chemistry, and welcome to this video on aromatic chemistry, and this one is dedicated to AQA. So this video has everything you need to know for AQA and is designed specifically around the specification for AQA. So if you're studying this exam board in A-level, then this is perfect for you. So there's no generic information in here. Everything in here is dedicated to AQA. There is actually a full range of these revision videos on Allery Chemistry YouTube channel, so just go and have a look there as well. There's loads of information on general chemistry as well. There's the whiteboard tutorials. There's some information on there's videos on Allery Chemistry there, and also I've done some past paper walkthroughs as well, so it's quite a comprehensive range of stuff for general information and specifically to this board. It's all for free, so all I ask is you hit the subscribe button. That would be absolutely fantastic, just to show you support for the channel, because as long as people keep subscribing and watching the videos, then I will keep on making them and updating them and try new things, etc. So go and have a look on there. If you would like to purchase a copy of this, these are just slides that I've made for revision purposes, but if you'd like to have a copy of these, then you can purchase them on the link below in the description box. They're great value for money, and you can use them on the move, on your smartphone, your tablet, use them on the bus, etc. Wherever you're traveling to, all that information's there, and you can move it around at your leisure. And I know some people have also printed these off and used them as revision notes. So if you want to copy them, click on the link below and you can get a hold of them. The full series is available there. Okay, so like I say, this is dedicated to AQA, and so therefore it meets the specification points that you can see on there. So we're going to look at two main aspects of this. It's quite a relatively short video for this one. We're going to look at bonding, which is mainly to do with benzene and delocalized electrons, and then we're going to look at some reactions of benzene as well, so electrophilic substitution reactions. So that's pretty much the order of play for this video. Okay, so now we're going to look at, the first thing we're going to look at is benzene. Okay, so benzene is a cyclic compound. It's planar, so there's no bits sticking out of it, so it's just a flat molecule, and it has the formula C6H6. So it has, carbon has 4 valent electrons, okay? Each carbon is bonded to 2 other carbons and 1 hydrogen atom, okay? And so the final lone electron is in a p orbital, which sticks out above and below the planar ring. So you can see here that we've got our carbon atoms here, okay? 1 electron is used to bond to hydrogen, as you can see there. 1 electron is used to bond to a neighbouring carbon, and again on this side. And then the valent electron that's left over, is then in a free orbital that goes above and below the actual planar ring. Okay, so that's the basic structure of benzene. Now we know that actually these lone electrons and them lone orbitals, they actually combine together to form a delocalized ring. It looks a bit like a donut. So you can see here that you've got the electrons that were in here, they kind of overlap. They kind of overlap all the way around, and they actually share the electrons and distribute it equally around the benzene ring. And now that actually gives it a unique property. It gives it a little bit of strength. But because of that delocalized electron structure, actually all the bonds, all the CC bonds are the same length, okay, which is 139 picometers. Okay, so that's exactly the same length. There isn't any longer or shorter ones. Now, that actually sits somewhere in between a single and a double bond, which gives it a very unique property, because you can see there that a single bond is 154 picometers, and the double bond's a bit shorter at 134 picometers. So at 139, that sits somewhere between a single and a double bond, and so that obviously gives its rise. That's give rise to the the delocalized structure in the benzene ring. Okay. So benzene, obviously we've drawn the molecule there with all the orbitals coming in and out and the delocalization of that, but benzene actually is quite difficult to draw if you're drawing it like that. So thankfully we can use a skeletal formula, and the skeletal formula is then used to draw benzene, and you'll use this formula all the way through organic chemistry at least. So the structure, there's 2 ways in which you can draw it. One, which is the most common way that you are expected to draw in at A-level, but there is one which sometimes is drawn to show reactions. Sometimes it's easier to draw it in this way, and this is actually called Kekulé's structure. So it was named after a fella called Auguste Kekulet, who basically thought that you had single and double bonds in a benzene ring, but actually that these double bonds, single and double bonds, as you can see there, would alternate alternate across the benzene ring, so they'd keep changing around and around and around like that. So you may see it drawn differently though, and this is probably the more likely way you're going to see it in your exam, which is with a circle in the middle, and that basically shows the delocalized electron system. And in fact, that's the one really you should be using for A-level. It's just so that you're aware of Kekulé's structure, because you're going to use it later to prove whether a structure, to prove the current structure of benzene. So basically, you'll see you have a circle in the middle that just represents the delocalized electrons in the benzene ring, and that's what benzene is. So remember that there is a hydrogen attached to each one of them carbons. It's very easy to forget what carbons and hydrogens you've actually got when it's in a skeletal formula, as you can see there. So you can see we've got carbons all at these points here, and we've got hydrogens coming off around the side, but obviously we don't represent them in a skeletal formula. They do exist, they are there, it's just we don't actually draw them in the skeletal formula, but just be aware that they do, that they are there, because this is going to be important when we look at mechanisms later on. So Friedel-Crafts and nitration, you need to be aware that there is actually a hydrogen there, we just don't show it in a skeletal. Okay, so now what we're going to do, obviously we know about the structure of benzene, and we know the type of bonds that they've got. It's kind of halfway between a single and double bond, and it's delocalized electrons. So that's quite a unique property in its own right. But with that property actually comes stability. And what you're expected to be able to do is demonstrate why benzene is stable, basically. And it's all to do with bond enthalpies. So actually benzene is more stable than the theoretical alternative, which is cyclohexane-1,3,5 triene. That's basically the Kekulé model. Okay, so Kekulé said that you had these three double bonds and they alternated around. Okay, so we're basically going to compare, we're basically going to prove in this case that we do actually have a delocalized system and not three double bonds. We don't have three double and single bonds. So all to do with bond enthalpy. So we measure the stability, like I say, by measuring the benzene, or measure the stability of benzene by comparing the enthalpy change of hydrogenation in benzene and in cyclohexane-1,3,5 triene. So basically, hydrogenation is adding hydrogen to a molecule. And of course, we can do that with alkenes, and you will have seen that in the alkenes topic as well, where we can add across a double bond. So we can measure the energy change for that. Now, you can see that if we hydrogenate cyclohexene, okay, so it just has one double bond, and we have an enthalpy change of minus 120 kilojoules per mole. So that's the enthalpy change of hydrogenation. So we're adding hydrogen to one double bond. Now, you might think, okay, well, if the structure of benzene had three double bonds, then surely we just multiply that by 3. And in fact, we do. So you can see, if we multiply that by 3, in theory, we should have an enthalpy change of hydrogenation of minus 360 kilojoules per mole. Okay, so that's very important. So it's minus 360 kilojoules per mole is the enthalpy change of hydrogenation if we had 3 separate double bonds. However, okay, so when we measure the enthalpy change of hydrogenation for benzene, it comes out at minus 208 kilojoules per mole. So obviously this is the experimental value. This is what we test benzene, we hydrogenate benzene, and that's the amount of energy that we come out with. So it's a lot lower than what we would expect if it did have 3 double bonds. So you can see here, if we have 3 double bonds, the predicted energy is going to be minus 360 kilojoules per mole. But actually, when we do it to benzene, it actually comes out as 208 kilojoules per mole. So this is the experimental value, the actual value of what we do with benzene. So minus 208 kilojoules per mole. So the energy is required to break the bonds, and energy is released when we form them. So we know that already from year 1 chemistry. And so what this suggests is actually more energy is required to break the bonds in benzene than it is in cyclohexane-1,3,5 triene, because that enthalpy change, the exothermic part, it is less exothermic than the predicted value. So that's telling us that more energy is needed to actually break them bonds. Okay, so that lower negative value, so minus 208, is suggesting that more energy is required to actually break them bonds, and so therefore it is more stable than the theoretical value. And so this is because of the delocalized electron structure. So you need to be able to go through and write answers down to why benzene is more stable. You're using one of the reasons, which is the bond length is equal in all of them. The other reason is this. It's to do with proving the bond enthalpy, using bond enthalpy, and proving that actually it is more stable because it's less exothermic, which suggests that more energy is required to break the bonds in the first place, which is an endothermic process. So these are the types of things that you need to be able to explain to the examiner. Okay. Right, so what we're going to look at, because obviously this is the basics to benzene. We've introduced you to benzene here. We've looked at the electron delocalized structure, and we've looked at how we draw it. Now, what we're going to do moving forward is we're going to look at using benzene to name it. So look at the different types of derivatives of benzene, but also we're going to look at the reactions of them, such as Friedel-Crafts and nitration. But we'll come into that in a moment. So let's look at let's look at the naming of them, or the types of things that you can get from benzene. Now, we call these molecules arenes. Okay, so an arene is just what we call an aromatic compound that contains benzene. So aromatics, anything that contains benzene, and so an arene is just a molecule that contains a benzene ring. And they're named in two ways, which isn't helpful. But don't worry too much about this. You're not going to be asked specifically to name some obscure benzene compound. You're going to be asked to name some specific examples, and here they are. So first one, we actually name it with benzene at the end. So for example, you might have a halogen derivative of benzene, so we call this bromobenzene. We can also have methyl groups, such as 1,2-dimethylbenzene, so we just put benzene on the end. And of course, we'll have nitrobenzene. That's where you just put benzene at the end. So all of these examples here, so whether it's a halogen, a methyl group, or a nitro group attached to a benzene ring, we just put benzene at the end and whatever group's attached to it. So there are other ways as well, and it's actually using phenol. So these are named as if the phenol is actually the functional group. So phenol is a benzene ring with an OH on it. Okay, so anything with a hydroxy group, benzene with a hydroxy group in there is called phenol. So a classic example is phenylamine. So the amine one, you don't actually call it benzene. You don't put benzene in the end. So whenever you see an amine group bonded to a benzene, you call it phenylamine. Okay, so that's the specific example that you need to know. Okay, so let's look at, so we know what these arenes are, and we know some of the derivatives, as you can see there. We're now going to look at some of the reactions of arenes. Now, arenes have, because they have this unique property, okay, of a delocalized electron shell, or delocalized electron ring, should I say, they actually have a different type of mechanism. They undergo a different type of mechanism to what you would expect. So, for example, if you look at the alkenes topic, normally when you add, say if you add bromine to an alkene, so decolorization of bromine water, that's an addition reaction, okay, because you're adding to the double bond. Now, benzene doesn't have double bonds as such. It has a delocalized structure, so it doesn't actually undergo addition. Arenes actually undergo electrophilic substitution instead, okay? So the reason why it's electrophilic is because we have a high density of electrons in that ring structure, and this means that it's attractive to electrophiles. So remember, electrophiles are electron-loving species, so these are substances which will be attracted towards high areas of electron density. So that could be, for example, a double bond. So for example, if you're adding to an alkene, it'll be electrophilic addition. If you're adding to an alkene, obviously the main difference with benzene is substitution, but we're still using electrophiles for this one as well. So, but as we've seen, benzene's really stable. So unlike traditional alkenes, where you've seen the addition of, say, bromine to it, they don't undergo electrophilic addition reactions, as what this would actually disrupt the benzene ring, the stability of that. So remember, the stability in benzene comes from the actual delocalized ring structure. The other thing, I suppose, if you've seen my other videos that I like to use, is basically atoms, molecules, protons, neutrons, electrons, anything like that. They all want to be in the lowest energy state possible. They are incredibly lazy, okay? So they don't want to be in a higher energy state than they have to be. And you can see the same applies here. Benzene is more than happy being a stable molecule, and anything which is going to disrupt that, it's going to put up a bit of resistance. So this is why addition reactions do not happen, because we're disrupting the kind of harmony of the delocalized structure in benzene. So it's not going to react very easily. So they actually undergo, like I say, electrophilic substitution, and this is effectively where we've got the hydrogen functional group on the benzene rings. Remember, on these skeletal diagrams you don't show hydrogen, but there is a hydrogen on each one of them points. That hydrogen is substituted for the electrophile that we're reacting it with. Okay, and there's two types, like I said before, that we need to know. One is Friedel-Crafts Acylation, and the other one is nitration reactions. There's only two that you need to know, so it's fairly straightforward. Right, so what we're going to do is we're going to look at Friedel-Crafts Acylation first. So it's named actually after two fellas, and I'll show you who they are. Well, obviously Friedel and Crafts, but I'll show you that I've got their pictures here. It's always nice to put a name to a face to a name, isn't it? So, but benzene is widely used in pharmaceuticals and dye stuff. It is such an important chemical to use. We wouldn't have nowhere near the amount of drugs that we do today. If we didn't have, or we didn't understand about benzene, and we didn't know, its reactions or what we can do with it. The stability of benzene is a bit of a barrier because it means it's difficult to react. But thankfully, Friedel-Crafts came up with a reaction mechanism for acylation to help solve this problem. Okay, so here they are here. So it's Charles Friedel and James Kraft. They were French and American scientists. So handsome chaps there. So they came up with a reaction where an acyl group, okay, which is RCO, and you would have seen this acyl group in the carboxylic acid and derivatives video. So if you're not sure about that, then go and have a look at that video. But if it's added to a benzene molecule, okay, so after the acyl group is added, the benzene structure is actually a good bit weaker than what it was before, and then it makes it easier to actually modify it. So it's effectively trying to break into that benzene ring, add a chemical onto there, so add a functional group on there, and then once we've done that, then it makes it a lot easier to then add what we want to that benzene ring. So it's breaking the ring structure in the first instance that's difficult. Now, acid chlorides or acyl chlorides, as you will have seen, are incredibly reactive. Okay, they have a delta positive carbon and obviously delta negative chlorine and oxygen, if you've seen that in the video. However, that is not good enough to actually react with benzene. It's just not powerful enough. That delta positive charge is not powerful enough to break the benzene ring. So what we must do first, we must do a preparatory step first, and we must prepare a very strong positive charge, basically a carbocation, to actually attack this benzene ring, okay, for the acyl group. So it must have a proper positive charge. So we must conduct a reaction first. Now, what we can do is we can prep it by reacting it with a halogen carrier. So we use a halogen carrier such as AlCl3, okay, and you'll see why it's called a halogen carrier later. And this will produce a much stronger electrophile with a much stronger positive charge. It's a proper positive charge, not just a delta positive. It's a really strong positive charge. So we've created a very electron deficient molecule, and that is really going to have a go at the benzene ring because it's got loads of electrons. So in Friedel-Crafts acylations, what we do is we react an acyl chloride or an acid chloride with a halogen carrier, that's our AlCl3, to create our strongly positive electrophile. Okay, so let's have a look at this first. So like I say, to make that electrophile, we're going to use aluminium chloride. So AlCl3 is the halogen carrier, and we're going to look at how we make this. So the first thing is we get our acid chloride, there's our acyl chloride, and we're going to react it with our halogen carrier. Now the halogen carrier accepts a pair of electrons away from the acyl group, so it accepts that, and effectively it takes the chlorine, so it strips the chlorine from the acid chloride. This bond breaks and it bonds onto here, and so what we form is our carbocation, as you can see there. So there's our positive charge, very, very powerful electrophile because it's got a large electron deficiency. And there's our AlCl4 minus. As you can see here, this is obviously accept the chlorine to form this this negative charge here. Okay, so this stronger electrophile here, this positive charge, is now primed and ready to be introduced to benzene, where it can attack it and add on to the benzene ring. Okay, so you can see we've got this preparatory step first to make the very strong electrophile, and then we introduce it to benzene. So let's have a look. So now we've got our electrophile. We need to react it with benzene, like I say, and we're going to make something called a phenyl ketone. And this is obviously done under reflux because our substances are volatile, so we don't want to lose them. So we want to heat them up, benefit from the heat but not evaporate into the atmosphere. So we use reflux and we use a dry ether solvent as well. So here's the first step. So here's our benzene ring, and we've got our benzene ring and we've got our electrophile, which is at the top here. So there's our electrophile. So what's going to happen first is actually the delocalized electrons in this here first will actually be attracted to the delta positive carbon. So what happens is some of the electrons from here will now be lured over because this is powerful enough to actually react. So this is what happens here. So the delocalized electrons are attracted to the carbocation, and the two electrons move to form a bond. As you can see there's the bond, and the ring structure is now broken because we don't have many electrons. Now this isn't very stable, but this is just far too attractive for benzene to ignore. So so you can see we've got this delocalized structure that's been disturbed, so we have this positive charge there now. Very important point here when you're drawing this is your semicircular electron ring structure here should not extend beyond the adjacent carbons to the one that's been attacked. So this is the one that's been attacked. Your adjacent carbons are here. So this ring must not extend beyond that. Very, very important. You've got to draw it carefully. Okay. If you do, you may lose a mark. So you've got to be, vigilant for that. So this is obviously our intermediate that we formed here, and there's our phenyl group that's been, or acyl group, should I say, that's been attacked or attached on here. The hydrogen we've now shown because it's going to play an important role. So here's our intermediate. Now we have our halogen carrier that has the extra chlorine on there. Okay, so it has this extra bit on here. So remember we formed that in the previous step. So what happens is the electrons from here actually now start to form a bond here with the hydrogen. Obviously this bond then breaks, as you can see there. Okay, and so effectively the chlorine then reacts with the hydrogen to form HCl. There it is. There's your HCl. And obviously we'll form our catalyst back again. Just before, so I've jumped ahead there a little bit. So the electrons obviously jump on here, but then this bond needs to break. So it's the electrons in this HCH bond here that then jump back into the ring structure and it reforms it fully again. So we've now got a stable ring structure that's been formed. But crucially, we've now got our functional group that we've added onto our benzene. So you can notice that the catalyst has actually been reformed here, and the reason why it's called a halogen carrier is you can see it's temporarily carried the halogen from the acid chloride and it's given it to the hydrogen, and obviously we formed this here, so it's reformed. Very important because it's a catalyst, so it must be reformed. Okay, so you can see here there's two steps to this. It's first of all making your very powerful electrophile using a halogen carrier, and then it's using that to break the electron delocalized electron system in the benzene, and then that's reformed at the second step when the halogen carrier is then reintroduced, as you can see here, and obviously always show that your catalyst has been reformed. Okay, right, so there's one more mechanism that you need to know, and this mechanism is the nitration of benzene. Okay, so nitrating benzene is useful because it allows us to make dyes for clothing and explosives, so that's always useful, of course. Now, just like with the previous step with the Friedel-Crafts reaction, we have to make a powerful electrophile first. It's no good just using say something like nitric acid and just reacting it with benzene. It isn't going to happen. So basically, we must form our positive electrophile first. So what we need to do that is, like I say, if we heat benzene with concentrated nitric acid and sulfuric acid, we will form nitrobenzene, but we must form our electrophile first. So actually, this is done in two steps for the nitration of benzene. So the first step is to make the electrophile first, and so all we do is we react nitric acid with sulfuric acid, and we form these two ions here. Okay, now you can see a bit strange because nitric acid has actually, you can see here HNO3 has actually accepted a proton, so is actually a base. Even though we call it nitric acid, it's actually acting as a base here because it's accepting a proton. Remember the acid-base topic where you look at the acids, basically the definition of an acid and a base of the Bronsted-Lowry theory, so mine went blank there, the Bronsted-Lowry theory, where we say that an acid is a proton donor and a base a proton acceptor. Well, this is applying that same principle. So H2SO4 is actually an acid because it's donating a proton. You can see it's lost it there. So we formed these first, and then the second step, actually, the second step with this is then the H2NO3 decomposes to form that nitronium ion, NO2+. And that is our electrophile that we're going to use. So you can see it's got that positive charge, just like with the Friedel-Crafts reaction. We must form this first. It's no good just using that, because that's got, it's nowhere near positive, nowhere near powerful enough. So we form this nitronium ion here, okay, and obviously water. Now, just be vigilant. You can say, well, what happens with this then? You've got this HSO4 minus. You'll find out later, okay? You'll see in the next slide. Okay, so now we've got to use that nitronium ion that we've just made and react it with benzene to produce nitrobenzene. Okay, so let's draw our benzene ring here, and you can see we've got our nitronium ion here. Exactly the same as your Friedel-Crafts. So your electrons are going to move from this delocalized ring structure towards the NO2+. So let's have a look. There it is. Okay, so it's attacked by the benzene ring. And obviously we form that positive charge, remember, in there. Just remember that the delocalized structure here, this must not extend beyond the adjacent carbons of the carbon that's been attacked, okay? Just another point, just remember that. So then, obviously, we've got our intermediate, as you can see there. Now, the electrons on the CH bond move to reform the delocalized electron ring. So these reform that ring because it's positively charged. And then what we have is nitrobenzene that's been formed, okay? Now notice you've got the hydrogen that was on the benzene ring is now floating around. This hydrogen here, H+, reacts with the HSO4 minus that was produced in the previous step, if you can remember that, and that forms H2SO4 again. So that proves that sulfuric acid in this reaction is indeed the catalyst. It's a catalyst because it's been reformed. It's not actually being used up, okay? Now, the conditions of this reaction are really important because if we heat this reaction up above 55 degrees Celsius, we actually get multiple nitration of the benzene ring, and you end up something which could potentially be quite explosive. So we've got to be very careful with this, but a temperature below 55 degrees will ensure a single nitration substitution. So you're very important, keep it below 55 degrees. You do this reaction in an ice bath. You might have done this reaction with with a derivative of benzene. You wouldn't use benzene because it's carcinogenic, so it causes cancer. It's been banned in schools and colleges in Britain, so you're not allowed to use benzene, but you'll use a benzene derivative, so it'll have a group already attached on, which is safer to use. But nonetheless, if you've done this reaction, it's a vigorous. It heats up quite quickly. And you've got to make sure that the reaction that you're doing it in is, or the reaction that you're conducting is submerged in an ice bath to keep the temperature below 55. Otherwise, you end up with multiple nitration. Okay. Right. So, the nitro, like I say, about the uses of them, nitrobenzene compounds, they can be used to make various products that we use in everyday life. So this is, in particular, looking at the nitrobenzene compounds. So the first one, as we've said already, are dyes in pharmaceuticals. And these can be made by reducing nitrobenzenes to aromatic amines. So using a reducing agent such as sodium borohydride, and the benzene with the amine groups attached. So that's your nitrobenzene, and that's used quite a lot in dyes in particular. So you form azo compounds. You don't need to know much about them in at AQA. So you just need to know that they can be reduced to form your phenylamines, and then that's then used to make dyes. And another one is quite a nice one. This is the explosives. If you have toluene, so toluene is just benzene, it's the old-fashioned word, but toluene is benzene with a methyl group. Okay, so it's methylbenzene is the IUPAC name for it. But if we do multiple nitration of this, in other words, if we react this with sulfuric acid, nitric acid, and then do that reaction over 55 degrees Celsius, we will get multiple nitrations here, and this is why it's lethal, really, because if you form that, this is TNT, so trinitrotoluene. So toluene is just methylbenzene, is the old-fashioned word for it, and this is an explosive, TNT. Okay, so you've got to be very careful with this, as you can see. So, but that's it. So there's nothing more that you need to know about aromatic chemistry on that. So there's obviously them reactions and the mechanisms there. So fairly straightforward marks if you know your mechanisms, but the mechanisms are the same. We're just using nitration and Friedel-Crafts, except the Friedel-Crafts use an acid halogen carrier. Like I say, there's a full range of videos on AQA like this for year 1 and year 2 on Allery chemistry. There's also whiteboard tutorials, and there's also exam past paper walkthroughs. They're all for free. All I ask is you hit the subscribe button. That'll be absolutely fantastic just to show your support. And you also get all the updates as well. And if you want to purchase these, like I said at the start of the video, you can click on the link below and you can get a hold of them there. They are absolutely great value for money. But that's it. Bye bye.